Hello all, in today's lecture we are going to see about magnitude comparator. What is magnitude comparator? As the name implies, comparator meaning you're going to do a comparison of two numbers. Magnitude comparator implies you're going to compare the magnitude or the amplitude of your input signal to give your output. Clear? This magnitude comparator is again an example for your combinational logic circuit. Now, what is a magnitude comparator? Magnitude comparator is again an example for your combinational logic circuit. This magnitude comparator, it is mainly used to compare the amplitude of input signals. To give your output. Is it clear? Now, let's see how to design this magnitude comparator using combinational logic circuit. Whenever you see the word design using combinational logic circuit, what are the four basic steps that should come to your mind immediately? First is your block diagram. You have to draw your block diagram. Followed by, you have to draw a truth table. And from your truth table, you have to derive your Boolean expression. For that, you will be making use of your K-map. And from your K-map, you will be deriving a Boolean expression. After finding the Boolean expression, what is the last step? You have to design using logic gates. Clear? These are the four basic steps for all the circuits. Whether be it half adder or be it full adder, half subtractor, full subtractor, magnitude comparator, multiplier, whatever might be the circuit they're asking. If you see the word design using combinational logic circuit, then all these four steps has to be there in your answer. Clear? Now, let's see how to design your magnitude comparator using combinational logic circuit. What is your first step? You have to draw a block diagram. How do you draw a block diagram? Let this be my magnitude comparator. Let me take 1 bit magnitude comparator for now. Now, for 1 bit magnitude comparator, I'm going to give two inputs. These are my inputs. Let my input be A and B. So, with two inputs, say for example, let my inputs be A and B and I'm going to take two numbers. Let me take 6 and 4 as my input. Now, there are two numbers here. With two numbers, how many different possible combinations of comparison can you make? Normal mathematical comparisons you can tell me. One, you can check whether A is less than B, right? What is the other possible combination? You can also check whether A is greater than B. The other possibility is whether A is equal to B, right? These are the three possible ways you are going to compare between two numbers. The same is what we are going to implement it here. Magnitude comparator is also going to do the same comparison, but for input binary bits. Clear? Let's see how to do it. So, how many outputs we got here? One is for A less than B, one is for A greater than B, and one is for A equal to B. So, these three are going to be my output for your magnitude comparator. Is it clear? Now, we are done with your block diagram. What is the next step? You have to draw a truth table. We know our input, we know how many outputs we have. So, we can take it to a truth table. How many inputs I have? I've got two inputs, A and B. And how many outputs do I have? I've got three outputs. One is A less than B, A greater than B, and A equal to B. I've got three outputs. Clear? Now, if I have got two inputs, then how many combinations are possible? How do you find out that? If the number of inputs is equal to 2, that is n is equal to 2, then how many combinations will I get? How do you find out that? That is based on the formula 2 power n. So here n is 2. So it is 2 power 2, you get 4 combinations. That is, it is from 0 to 3. Clear? Can we write down the combinations in binary numbers here? So it is 0, 0, 0, 1, 1, 0 and 1, 1. Give the equivalent decimal number, it is 0, 1, 2 and 3. Clear? Now, we have got our input and we have to find out our output. How do you find out your output? There is only one condition here. Check all the input combinations. Whichever comparison condition is getting true, against that particular output you have to mention 1. If the condition is false for that particular comparison, then put a 0. Clear? Now, let me explain it better here. Take out this particular combination, the first combination. Here A is 0, B is 0. What do you observe from here? Both are equal. So A is equal to B. So against A equal to B, you will put a 1. For the other outputs, you will be mentioning 0. Is it clear? Whichever condition is getting true, only against that particular comparison output, you will mention 1. For the other comparison outputs, you will mention 0. Is it clear how to fill the truth table? Now, let's check with this particular combination. Here, now A is equal to 0, B is equal to 1. We have to do the comparison only based on A. Clear? Now, for this particular input combinations, what do you observe? Here, A is 0, B is 1, which means A is less than 1. So, against A less than B, you will give your output as 1. Is it clear? For the other outputs, you will mention 0. Now, let's do for the next combination. Take out this particular combination. Now tell me, A is 1 and B is 0. Talk with respect to A. Now, what do you observe from here? A is greater than B because A is 1 and B is 0. So, A is greater than B. So, against which particular column will you mention 1? It is against A greater than B. So, against A greater than B, you will put a 1. And on the remaining outputs, you will mention 0. Is it clear? Now, let's try out with the next combination. For this particular combination, both are 1. So what do you observe from here? A is equal to B. So against A equal to B, you will mention 1 and on the remaining outputs, you are going to mention 0. Is it clear how to draw your truth table? Based on the input combinations, you have to check whichever condition is getting true. On that particular comparison output, you will mention 1 if that condition is true. For the other comparison outputs, you will mention 0. Clear? Now, we are done with our truth table. So, what is the next step? You have to find out your Boolean expression. How do you find your Boolean expression? You have to take your output to your K-map. Clear? Now, how many outputs do we have? We have got 3 outputs. A less than B, A greater than B, A equal to B. All are 3 different outputs. So, how many K-maps will be requiring? You'll be requiring 3 K-maps. Clear? Let's do the K-map now. This is for A less than B. Similarly, you need another K-map for A greater than B and you also need another K-map for A equal to B. Clear? Now, how many input combinations are there? Which variable K-map will you be using? That is dependent on your input. So, how many inputs you have got? You have got 2 inputs. So, which variable K-map you will be using? 2 variable K-map. Based on your number of input, you will be deciding which variable K-map you want. If you have 2 inputs, so you will be using 2 variable K-map. Clear? Now, A. Here again, by default, it is SOP. Now, how do you position the numbers inside the K-map? This is for A less than B. Let's do A less than B now. Clear? For positioning the numbers inside the K-map, you have to check on your output. Wherever you have got your output as 1, you have to check the corresponding decimal number and against that particular decimal number whose output is 1, on that decimal number you have to mention 1 in your K-map. Clear? Now, check for A less than B. Where all have you got output? 1. You have got output 1 only in one place. So, check for a corresponding decimal number. It is number 1. So, against 1, you have to mention 1. Is it clear? Now, it's a single variable mapping. Give me the equation for A less than B. A less than B, it is equal to, by default, it is SOP I told. So, 0 will be represented by complement, 1 will be represented by actual variable. Here, all these terms corresponds to the letter A and all the digits on your horizontal corresponds to the letter B. So, I will be mentioning it like this. Clear? Now, what is A less than B? You have to check horizontal as well as vertical. It is A bar and B for vertical. Vertically, it is A bar and on horizontal, it is B. So, I have included both. Is it clear? This is the Boolean expression for A less than B. Now, in a similar way, you have to find out for what is A greater than B also. For that, what you do? You have to check on your output. Wherever you have got your output as 1, check for the corresponding decimal number and against that particular decimal number which has got your output as 1, mention that particular decimal number as 1. You have to position that number as 1 in your K-map. Clear? Now, let's do for A greater than B. Where all have you got output 1? You have got output 1 in only one place. So, which is that number? Check for the corresponding decimal number. It is number 2. So, against 2 in your A greater than B K-map, you have to mention 1. Is it clear? Now, do the mapping for this again. What is the output? A greater than B is equal to, here again, this is A bar, this is A, this is B bar and this is B. So, what is the output? It is A and B bar. Clear? Now, coming to A equal to B. Here again, the same case. Check for your output. Wherever you've got 1 on your output, check for the corresponding decimal number and against that particular decimal number, you have to position 1 in your K-map. Clear? Now, we are doing it for A equal to B. Where all have you got 1 as your output? You have got 1 here, you have got 1 here. So, check for the corresponding decimal number. Here it is 0 and here it is 3. So, against 1 and against 3, you will be positioning 1. Now, do the mapping. What is A equal to B? A equal to B is nothing but this is A bar, this is A, and this is B bar, and this is B. So, my equation will be A bar B bar plus AB. Clear? What gate is this? This is nothing but my XNOR gate. Clear? Now, we are done with our K-map. We have found a Boolean expression also. What is the final step in your designing procedure of combinational logic circuit? After finding the Boolean expression, you have to design it using logic gates. Now, let's see how to design using logic gates. Now, let's design it for A less than B first. A less than B is what? A bar into B. So, A I have to make it as A bar, I have to feed it inside a NOT gate. Clear? The output of this particular NOT gate. NOT gate is also called as an inverter gate. So, whatever input you are giving, my NOT gate output is going to invert my input and give. So, if I give A here, my output will become A bar. Clear? Now, I have got A bar here, A bar and B. Both are in product terms. If it is in product term, which gate should I use? I'll be using my AND gate. So, what is the output of this? This is A bar B, which is nothing but A less than B. Is it clear? Now, we are done with designing A less than B output. Go for A greater than B now. What is A greater than B output? It is A into B bar. I have A already here. So, let me take A from here and B is in complemented form. So, I have to convert this B to a complemented form. For that, I have to feed it inside a NOT gate. Clear? What is the output of my NOT gate? It has become B bar. Now, A and B bar. These two are product terms. So, which gate should I use? I'll be using my AND gate. So, what is the output of this? This is A into B bar, which is my A greater than B output. Is it clear? We are done with designing A greater than B and A less than B. What is left? We have to design A equal to B. What is A equal to B? It is nothing but my XNOR gate. So, try to design that. So, that is A. A I already have. So, let me extend A from here. And what is B? B, I already have it here. So, I'm just going to extend the line here. These two inputs, I have to feed it inside which gate? This is XNOR gate. This is my XNOR gate. This is nothing but A equal to B. Clear? This is how you'll be designing a magnitude comparator using combinational logic circuit. Understood? This is your 1-bit magnitude comparator. What do you mean by 1 bit? Because you're doing comparison of only 1 bit here. Clear? Let's sum it up. In today's lecture, we saw what a magnitude comparator is and how to design your magnitude comparator using combinational logic circuit. How do you design? Whenever it comes to designing, these are the 4 basic principles that you have to keep in mind. First step, you have to draw a block diagram depending on how many bit magnitude comparator they are asking. Clear? If they are asked for 1-bit magnitude comparator, then you'll be designing like this. In case if they're asking for 2-bit magnitude comparator, that we'll say it in the next lecture. Clear? Now, after drawing a block diagram, we have to draw a truth table as well. And in a truth table, based on the input, we'll decide how many combinations you want. And based on your input combinations, we'll decide on how to find your output. That is only based on only one condition. If the input combination is getting satisfied with any of the comparison output, against that particular output, you'll be mentioning 1. If the condition is getting false, then you'll mention 0. Clear? Now, after finding your output, what is the next step? You have to find your Boolean expression. For that, you'll be taking your output to your K-map. Do the positioning, do the mapping, and then finally get a simplified Boolean expression. What is the last step in the design procedure of a combinational logic circuit? After finding a Boolean expression, you have to design it using logic gates. This is how you'll be designing a magnitude, 1-bit magnitude comparator using logic gates. Clear? I hope you're clear with this lecture. If you find my lecture useful and informative, like, share and subscribe to my channel. Thank you.